Now, at some point, you might also want to calculate the second derivative using discrete points. And the second derivative is just the derivative of the first derivative. So your second derivative, which is d squared y dx squared, that's defined as the limit as delta x goes to 0 of the delta in dy dx divided by delta x. So how would we calculate the second derivative? The formula is a little bit more complicated. It's not as easy as just a delta y over delta x. You have to have a delta in dy dx over delta x. So how does that look? So the way I like to think of it is, let me go ahead and imagine that we have points, we have discrete points, right? I plus 1, I minus 1, etc. Let's imagine that we have points I plus a half and I minus a half. Now these points don't really exist, and that's why I'm putting them in quotes. But if we imagine that we have those points, then we can say, all right, d squared y dx squared evaluated at I is approximately equal to our first derivative, dy dx, evaluated at I plus a half, minus our first derivative, dy dx, evaluated at I minus a half, all divided by xi plus a half minus xi minus a half. And now that we have that, what I'm going to do is I'm going to take the numerator, which is composed of two first derivatives, and I'm going to apply the finite difference approximation to each of those. So this becomes approximately equal to yi plus 1 minus yi over xi plus 1 minus xi. So before I move on, what I've done here is I've taken this first derivative, evaluated at I plus a half. So at some imaginary point between I and I plus 1, and I've approximated the derivative using a central difference formula, because this I plus a half should be halfway in between I and I plus 1. So this is a central difference formula approximation of that evaluation of the first derivative at I plus a half. I can do the same thing, another central difference formula for dy dx evaluated at I minus a half. And since its central difference will be symmetric around I minus a half, then you have yi minus 1, all divided by xi minus 1. That is all divided by the same denominator that we had before, xi plus a half minus xi minus a half. Again, these are still imaginary quantities. Or not imaginary, but they're fictional, right? Okay, so the thing that makes this a lot easier is if your x's are spaced out equally. If your x's are spaced out equally, then each of these differences in x, they're just some delta, these differences in x are just some delta x. And so when we work this all out, assuming all of these delta x's are equal, what we get is our second derivative, d squared y dx squared, evaluated at I, is equal to, if I look in the numerator here, I have a positive I plus 1 and a negative yi, a negative yi again, and now a negative times a negative makes a positive, yi minus 1. And so in the numerator here, I'm going to have yi plus 1 minus 2 yi plus yi minus 1, and all of that is divided by what we have in the denominator is a delta x here. These two are, they combine because you have the same denominator in two fractions that are added together, or in this case subtracted. So this is just one delta x, and then you have another delta x. So what they do is they combine to give you a delta x squared.